Hey everyone, and welcome to this explainer. Okay, today we're diving into something you probably have in your ears right now, and maybe occasionally lose down the side of the couch. True wireless stereo, or TWS earbuds. We're going to unpack the incredible, almost microscopic engineering that makes these tiny devices possible. But we won't just stop at the shiny exterior. We're going to explore the hidden trade-offs of their shrinking size, tracing their entire technological life cycle from the initial design table all the way to the end of their usable life. Here's our roadmap for today. We'll start with the anatomy of an earbud, then look at keeping the water out, over-the-air lifelines, fixing broken connections, and finally wrap up with the repairability crisis. Let's get right into it.
Section 1. Anatomy of an earbud. The brains behind the buds.
To really grasp how these things work, we got to shrink ourselves down. I mean, way down. The spatial and power limits that audio engineers are up against, they are absolutely extreme. Just think about the sheer complexity of a TWS chip. You've got RF basebands, audio subsystems, computational buses, literally all jammed together on a tiny piece of silicon. The audio processor alone is handling a massive load. We're talking running 128 tap filters just for active noise control. Basically, that means the chip is doing insane real-time math to cancel out the noise around you. And the craziest part? That whole blueprint is barely a few millimeters across. And that brings us to the golden rule of chip design, PPA. That stands for power, performance, and area. You can think of PPA as the ultimate engineering constraint. It is this constant, fierce tug-of-war. Look, if you want higher processing speed, that's the performance, you're going to need more battery power, right? And more power usually means a bigger battery area. But with an earbud, every single millimeter of space, every tiny milliamp of battery life is fiercely negotiated. You can't just slap a bigger battery in there because, well, it literally wouldn't fit inside your ear. So how in the world do engineers win this PPA tug-of-war? Well, one major game changer involves using custom extensions within a RISC-V architecture. It's kind of like giving the processor a highly specialized, custom-built tool belt instead of just a generic one. By doing this, the chip can do the heavy lifting, like that crazy intensive noise cancellation we just talked about, but using just a fraction of the energy. Engineers are able to drastically cut down power consumption while keeping top-tier audio performance. And get this, it doesn't even add to the hardware costs. Pretty brilliant, right?
Now, beyond that main brain, there's a whole supporting cast making the magic happen. Take the charging case, for example. It relies on these low-cost, specialized microcontrollers like the Texas Instruments MSP M0. These little guys monitor the battery health and control the charging box, all while drawing less than 1 single microamp of power in sleep mode. That is basically a microscopic sip of battery life. Throw in some highly efficient power management ICs, handling simultaneous dual-path charging, plus these tiny MEMS microphone arrays, and you've got this beautifully orchestrated microsystem just working in perfect harmony.
Moving on to Section 2, keeping the water out, building the armor.
So we've got these delicate, tiny computers, but we expect them to survive our sweaty gym sessions and unexpected rainstorms. How do manufacturers actually seal them up? Well, as we look at how these IPX water resistance ratings scale up, you'll see the engineering gets pretty intense. Down at an IPX4 rating, you might just see basic silicone gaskets and some acoustic mesh. But jump up to IPX7, where the bud can literally survive being completely submerged underwater, and the manufacturing completely transforms. Manufacturers rely on advanced materials like PTFE mesh, hydrophobic conformal coatings sprayed right onto the circuit boards, and even laser or ultrasonic welding to seamlessly melt the plastic shell together. It's serious armor.
Which leads right into Section 3, over-the-air lifelines. The digital connection. Now here is a really fascinating paradox. If a device is literally laser welded shut to keep the water out, how on earth do you fix a software bug? I mean, it's not like you can just plug a USB cable directly into the chip anymore. You have to rely entirely on over-the-air or OTA Bluetooth updates. But remotely updating firmware is risky business. If your connection drops halfway through, you could completely brick or permanently kill the earbud. This dual-core architecture shows us exactly how they avoid that disaster. Chips like the STM32WB physically isolate the user application, which runs on a Cortex-M4 core, from the critical wireless and security tasks running on a separate Cortex-M0 Plus core. Because of this strict memory isolation, even if your remote update completely fails mid-transfer, that core wireless communication doesn't get corrupted, so your device stays safe and alive.
All right, on to Section 4, fixing broken connections. The midlife crisis.
Okay, we've geeked out over the pristine engineering,
But let's pivot to the real, everyday consumer experience. Because we all know that incredibly frustrating midlife crisis moment when your high-tech earbuds just inexplicably refuse to work. Have you ever opened your phone's Bluetooth menu only to see your left and right earbuds listed as totally separate devices, and sound is only coming out of one ear? It is a massive pain point. Actually, over 8.7 million people search for troubleshooting advice on this exact issue every single year. You are definitely not alone.
To figure out how to fix it, you first need to understand the master-slave architecture. In most setups, one earbud, usually the right one, acts as the master receiver. It grabs the signal from your phone and then wirelessly relays that audio stream over to the slave earbud. It's essentially the boss and the worker. So, when they suddenly stop working together, the root problem actually isn't your phone's Bluetooth at all. It's actually corrupted internal pairing tables inside the earbuds themselves. That vital master-slave link between the two buds has just broken.
And that, right there, is exactly why the generic advice of just restart your phone almost never works. To actually fix this, you have to execute a true engineering-level factory reset. First things first, make sure the pins are clean and the buds are charged up past 30%. Second, execute the specific hardware button hold for your model to force the LEDs to flash. This physically clears their internal memory. Third, completely forget the device on your phone. Delete it entirely. And finally, and this is the absolute crucial step, take them out of the case and wait a few seconds. You have to let the earbuds re-sync to each other first. They need to rebuild that master-slave link before you ever try introducing your phone back into the mix.
Section 5. The Repairability Crisis. The End of the Line.
So the very same engineering that gives modern earbuds their amazing durability against water, the incredibly tight tolerances, the ultrasonic welding, the glue, that same engineering creates a really stark problem when the fragile internal lithium battery eventually dies. Let's look at the teardown facts gathered by iFixit to see where the industry is heading. When you compare the older Sony WF-1000XM3 to the newer XM5 model, the shift is pretty undeniable. The older XM3 actually featured a standard button cell battery and modular JST connectors, which made it incredibly repair-friendly. But the newer XM5? It features tightly glued halves and batteries that require expert-level microsoldering just to swap them out. It severely limits accessibility for any kind of typical DIY repair.
This really brings up an ongoing tension in the tech industry. As consumers, we overwhelmingly demand these incredibly small, feature-rich, waterproof devices. But those exact demands are exactly what drive the creation of sealed, basically unrepairable hardware that eventually just becomes e-waste. As iFixit notes, after all, we vote for the end product with our money. The best way to end the production of disposable electronics is really rather simple: stop buying it. It perfectly captures this really tough tug-of-war between advancing device functionality and actually ensuring consumer repairability.
Which leaves us with a final thought for today's explainer. As our portable electronics continue to shrink down to near-invisible sizes, what is the real cost of a disposable form factor? It's a fascinating question, right? It really asks us to consider the complete life cycle of the gadgets we wear every single day, from the brilliant microscopic RISC-V engineering that brings them to life, all the way to the environmental legacy they leave behind. Thank you so much for joining me to explore the hidden depths of TWS earbuds. I really hope this explainer gives you a whole new appreciation for the absolute engineering marvels sitting in your ears right now.